Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in the Department of Computer Science in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about graph theory concepts. So the very first thing is that the graph is a collection of points in a plane, so called as vertices or nodes. So which are going to be connected by means of a line segment, so which in turn called as edges or arcs. And this graph can be represented as uh, g of v comma e, where v should be the vertex and e should be the edge. So the graph is nothing but a collection of points in the plane, okay, or it may be called as a vertices or a nodes, what we call, and which is going to be connected by means of a line segment is called as an edge or ax. So there are different categories of graphs like a directed graph and what we called as a digraph, and undirected graph is another one. So digraph means that where the edges is going to maintain an arrows. So where the vertex u comma v may not equal to v comma u, whereas in undirected graph, which should be in ordered vertices like u comma v and then v comma u are same here, since there is no direction in between them. So we can able to write it as v comma u and then u comma v as well. Both are same here. So the category of the graph means so directed graph and undirected graph. So undirected graph means a digraph, which means that which is a where the vertices are going to be connected by means of edges, directed edges. And this one what we called as undirected graph, and this one what we called as a directed graph. The graph representation is that, so there are two ways to represent a graph data structure. So first one is adjacency matrix and second one is adjacency list. So normally mainly are going to represent a graph in the form of adjacency matrix, and a second option what we called as adjacency list. So how this adjacency matrix is that, so it should be a 2D matrix of the size n by n, which is going to be filled with either zeros and ones. So where I should be 1 whenever there is a vertex I and then vertex j are going to be connected. Suppose if this is the graph, in this graph, so I'm going to consider the number of vertices of 4. So that's why I'm going to consider along the rows and then columns. And in this I'm going to fill with either zeros and ones, so I can able to fill that. So I have an edge from a to b, so that's why I'm going to mark it as 1, and a to c, so I'm going to mark it as 1 here. So since there is no edge from a to a and then a to d, that's why it should be 0. And similarly, if I'm going to consider the b vertex here, so I have an edge from b to a and then b to d, so that's why it should be 1. And this is there is no edge from b to b and then b to c, that's why it should be represented as 0. And see here, in c what I'm going to say that is, so I have an edge from c to a and c to d, so that's why it should be 1 and the remaining all should be 0. And if I'm going to consider d here, so I have an edge from d to c and then d to b, so that's why it should be 1. So like this I can able to fill this adjacency matrix with zeros and ones. So similarly, this matrix is going to be different if I'm going to consider in directions. Suppose if in this directed graphs, how the adjacency matrix will looks like this. So I have an edge from A to B, so I have to mark it as 1, and A to C 1, and A to D is not there, so remaining all should be 0. So from if I'm going to consider B here, so there is no edge that is leaving from B, so that's why it should be all zeros. So if I'm going to consider C, there is no edges leaving, that's why it should be also zeros. And for D, I have an edge from A to D, and then sorry B to A, D to B, and then D to C, so it should be 1. So this matrix should be entirely different one. So when I'm going to consider this diagram here, adjacency list. So here adjacency list or graph or a diagram is a collection of linked list. So all its adjacent vertices are connected by an edge. For an example, what we're going to call it as this. And here in this graph, I'm going to represent in the form of an adjacency list. So this should be the adjacency list. So if I'm going to, so what are the edges that are connected with the A's, B and C? That's why B and C nodes are going to be connected to A. And for B, the A and D are connected, so A and D. So for C, it should be AD, and D, it should be B and C. So like this, I can able to represent this adjacency list, or what we call it as diagram. Uh, so all the adjacent nodes are going to be connected by an edge. And if I'm going to consider weighted graph here, so in this weighted graph, the adjacency matrix is going to be filled with weights values instead of zeros and ones. So that's why this should be called as weighted adjacency matrix. So if I'm going to consider the set of rows and then set of columns here, and whenever I'm going to have an weight, so A to B, I have weight value is 1, and for A to C it should be 2, and A to D it should be 5. So that's why I'm going to fill with the weight values. Similarly, if I'm going to consider B here, so B to A it should be 1, B to D it should be 4, and for C it should be C to A, and then C to D it should be 2 and 3, and for D it should be 4, 3, and then 5. So in weighted adjacency matrix, we are going to be filled with weight values of the graph. So weighted graph is the graph. So with the number is going to be assigned to its edges, and these numbers what we call as weights or costs. So the weighted adjacency matrix looks like this. So in similar fashion, how this adjacency list along with this vertices, we are going to consider the weight values also. Then comes to graph terminology. So here some of the basic terms we have to be learned in graph. So first one is that node. So in a plane, the collection of points we call it as a vertex, and this one also called as a node here. And edge. So edge is nothing but a line segment between the two vertices, and adjacent node means that so the node which is going to connect the near vertices, and degree of node means the number of edges that are connected to that node. So the degree of A equal to 2, so based on the number of edges. and degree of B is equal to 1 since there is only one edge that is connected. So here node is nothing but in a plane. So if I'm going to be a collection of points, what we call it as a node here or a plane, and here in this one, node may also called as a vertex or can be called as a point as well. And this in the line segment which is going to be connected the two vertices is said to be called as an edge, and this edge is sometimes called as an arc as well. And here this should be v1, v2, v3 and v4. So for this v1, so the v2 and v3 are adjacent to the vertices to the vertex v1, and then v2 and v3 as well are the adjacent nodes of the vertex v1. And degree of the node means here, so the number of edges that are connected to v1 is 3, so 3 is going to be considered. For v4 it should be 3, so 3 it should be also 3. So in this one what I'm going to say that is the so in this one the two edges are connected, so the degree of node A equal to 2, and the degree of C, there is only one edge connected, that should be 2, and degree of B should be 2 also, sorry 1. And next I'm going to say that is the size of the graph. So size of the graph means the total number of edges in the graph should be considered as size of the graph. So here the maximum number of edges is that 2, so that's why the size of the graph is 2. And next one is the path. So path is nothing but a sequence of vertices. So the path is nothing but the sequence of vertices from the start node to the end node. So suppose if what is the path from A to C, I want to find out. So what is the path may be A to B, and B to C is the path. Otherwise I can able to go A to D and then D to C. So this one should be called as a source, and this one what we called as a destination. And so in this one what is the path from suppose if I'm going to have on the graph like this. So what is the path from A to E? So for that we have to find, so A to B I can able to go, otherwise A to B to C, A to B, B to C and C to B. So this is one path, and second one A to B, B to D and D to E is on that path. And third one I can able to write it as A to D, D to B, B to C and D to E. So A to D, B to C and C to E. And another thing A to D and D to E is another path. And I can also go from like this. So these are the paths where I can able to reach from the source A to the destination E. And next one is the path length. So how can I able to find the path length here? So the total weight of the distance value obtained by a particular path of the starting node to the ending node considered as the path length. So it should be the summation of all the weights in the edges. So what is the path value from A to D? So that should be 1. A to B and B to D, this is the one path. So the cost value is 3, 1 plus 2. So A to B, B to D. So the cost length is that 1 plus 2, that should be 3. So another way I can able to also go some A to C and C to D also, where the path length is 7. So if I want to find what is the minimum, so the minimum should be A to B and then B to D. So it should be the summation of the weights of edges in the graph. Now next one is that connected graph. So connected graph means every vertices are going to be connected. A not connected graph means every vertices are not connected. So this should be the fully connected graph, and so this should be the partially connected graph. So if I'm going to join fully connected with the vertices, what is there in between them, then it should be considered as the fully connected graph. And next one, what is a cycle here? Cycle is the path of the source to the end at the same vertex, does not traverse the same edge more than once. And acyclic means a graph with no cycle is said to be acyclic. So the cycle is the path of the source to the end at the same vertex and does not traverse the same edge more than once. And cycle means that a graph with no cycle is said to be acyclic. A graph with no cycle is said to be acyclic, and a cycle which contains the path of the source to the end and does not traverse the same edge more than once, then it should be considered as the cycle. So in cycle, the source and destination should be same. So I have just now discussed the different types of graphs like directed graph. So all the edges are said to be directed, if the connection is symmetric. And directed graph means all edges are directed. If only if an edge implies one direction of connection. And weighted graph is the graph where the edge has associated numerical value for weight. So in undirected graphs, so the pair of vertices representing any edge is unordered, and the pairs UV and VU represent the same edge. So this looks like a tree, but tree is also a graph. So what are the set of vertices of the graph is that 0 to 6, and edges should be 0, 1, 0, 2, 1, 3, 1, 4, 2, 5, and 2, 6. So every tree become a graph here, but every graph may not become a tree. So undirected graph is said to be connected if there exists a path from every pair of vertices in the graph. And directed graph, so directed graph what we called as a digraph. So each edge is going to be represented by order pairs, and a directed graph is nothing but a sequence of distant vertices, such that if there is an edge from vertex, each vertex in the sequence to the next. And weighted graph is the graph where each edge has an associated numerical value, what we called as weight. And this weighted graph may be also directed one and undirected one, and the weight of the edge is often referred to as cost of the edge. An example of weighted graph is that, so looks like, so whenever the values are going to be assigned to each edge, then it should be treated as the weighted graph. So in weighted graph, it should be also two types. So this should be the undirected weighted graph, and similarly, if I'm going to consider an arrow, it should be considered as the directed weighted graph. So next we are going to discuss what are the graph traversal techniques. So normally the graph traversing means that visiting all the nodes of the graph, and if we want to visit every vertex and every edge exactly once in some defined order, so for that we are going to be follow two types of algorithms like breadth first search and depth first search. So these are the two primary traversal algorithms in graphs. So what is the breadth first search and then depth first search? In depth first search and breadth first search, normally we have to visit n, and we have to put this n children on the list, that may be either a stack or queue. And for each child in the C, so again we have to search a child node. If we want to use a stack and recursive, then we have to make use of DFS. And if we want to use this queue as an iterative, then we can able to get BFS. So in breadth first search, we have to make use of queue data structure, and depth first search, we have to make use of stack data structure. So traversing means visiting all the nodes exactly once in the graph. So for that two traversing techniques, we are going to use that. So first one is breadth first search and depth first search. So first we have to visit the node, and then we have to put the children of this node into a list data structure either in queue and stack, and again the children we have to search the what is the child of that. So let's see the first one, that should be breadth first search. So the idea is that we have to visit the children before the grandchild. So the visiting order is that, so first we have to visit the vertex and then visit all its neighbors, then visit all the neighbors of the neighbors. So the breadth first search is used as the first best shortest path in the given graph, and you should need the flags or some way to prevent the infinite loops. That should be the weakness here. So the algorithm is that first we have to create a queue, and then we have to mark this V as visited one and then put V into the queue. And similarly, while queue is empty, so remove the head of the queue and then mark all the end queue for all the neighbors of queue. So this is the algorithm what we are going to follow. So first initially how to define a queue, and then whatever the vertex we visited, that should be marked as visited one, and this one is going to be placed here. That should be V1, V2, V3 and V4. So what is next, until the queue is not empty, so we have to delete the head of the queue, and then we have to mark all the neighbors of V1. So what are the neighbors of V1, V2 and then V4, and this one is going to be removed, and then we have to be set it as marked. Then what are the adjacent vertices of V2, V1 already is there, and then V3 is not there, that's why I have to push onto the queue. And so this one also going to be as marked, and have to add it to the output. And for V4 it should be V1 already visited, and then V3. So V3 already in queue, so this one is going to be deleted, and this one also going to be deleted. So this should be the BFS order of the resulting graph. So let's take an example how we're going to construct this BFS. So first the starting vertex is A, and from A, so what are the vertices that are connected here? So B, and then C, and then D. So this one is going to be add on to the queue, right? And then next one, so what are the vertices that are connected for B, E and F? So this is going to be added into the queue. And next one, for C, there is no chase for this one. So next one is D. So what for the D? So Z. So that one is going to be pushed onto the queue. And finally, so there is no child for E and F, and only one child for F is there, that should be H. So like this, we are going to visit all the vertices in the graph by level or adjacent to that nodes. Okay. So in BFS, so first the starting vertex is A. So what are the adjacent vertices of A? You have to be visible. That should be B, C, and then D. Okay. So next after that, so of D, so for B, what is there? E and F. So that one I'm going to push onto the queue. So for C, no childs. For D, it should be G. So that's why I'm going to push onto the queue. And for E, there is no childs. And for F, it should be H. So H is going to be added. So when it comes to this depth first search, so it is an algorithm for traversing or searching a tree here. And once we're going to be started route, so we have to be selecting some of the nodes as the route in the graph and explore as far as possible along each branch and then before the tracking. So for this idea is that follow the single path to its end, then backtrack. So is an algorithm for traversing or searching a tree and then tree structure graph also. So once we are going to be start at root, then simultaneously select the nodes that are connected to the root in the graph and explore as far as possible and then perform backtracking again. So example is that so consider this tree. So for this, the what is the starting node? That should be one A. So for this one, so next whatever the nodes that are connected to A is that BCD, but only one thing have to be selected. And then what are the adjacent nodes for connecting to B is the E and F. So I'm also going to select E. So once this one is done, then again I have to be no chains are there for this one. So again I have to backtrack it. And then what are the vertices that are connected to B F, and what are the vertices that are connected to F, that should be H. So then I reach the maximum level. So that's what I'm going to do. Again I have to be backtrack to the original node and then select the next one, that should be C here. Again there is no more chairs here, so again I have to backtrack the original one and then select the next, that should be D and then G. So like this we're going to be select the depth first search. So in depth first search, what I'm going to say that is we have to be visit level by level of the vertices. So like so if I'm going to be start with the A, then I'm going to be select the next node, that should be B, or I'm going to select D as well, C as well, and the B is selected. What are the next level node? That should be E. So again I have to backtrack it since there is no change for E and F, and next one is that H. So once this one is done, again I have to go to perform the backtracking and I have to choose the next level node, that should be C, and again I have to perform backtracking and then I have to find the next level one, D and then G. So next, how are we going to calculate the time complexity and space complexity of this graph travels? So here the breadth first search and depth first search time complexity should be same. It should be a big estimate of V plus E. So where E should be the number of vertices in the graph and E should be the number of edges. And space complexity is that the BFS, it should be big estimate of mod V as well, since at worst you need to hold all the vertices in the queue. And then the space complexity should be depends on the implementation, recursive implementation, and the worst case for DFS will be the best case for the BFS, and the best case for DFS should be the worst case for the BFS. So these are the disadvantages of mainly this DFS, the space complexity need to be dependent, so it should be the big estimate. And finally, what I conclude that so graph is a linear data structure, non-linear data structure. So which is going to be connected by means of vertices and then edges, which is going to be connected by means of edge or arcs, where these edges may be directed one or undirected one. And the graph is represented by two important ways, that adjacency list and adjacency matrix. And this graph travels is the process of checking and updating each vertex in the graph. And the graph traversals means visiting each and exactly one node. And there are two graph traversals. So first one is breadth first search. So visit the neighbor vertices before the chain vertices. And breadth first search is used for traversing the finite graph. So finally, I conclude that so graph is a nonlinear data structure which is a collection of vertices and edges and should be represented in two phases like adjacency list and adjacency matrix. Most preferably, we are going to consider adjacency matrix here, and this graph traverses visiting each and every node exactly once, and there should be two graph traversals. So first one is breadth first search and depth first search. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.